Okay, this thing.
It's not here yet.
Really, still not yet
Yeah,
there.
now it's
So
here.
it's there.
So can we check this one?
Okay, mic check. So it's okay. So everything okay. So I'm hoping to close today's lecture a bit earlier than usually
Oh, okay.
because it's
So I can follow it.
yeah, you can follow it. And I'm really hoping that we can close it as early as an hour from now. An hour from now. So it's like 5:15.
Do you
Five.
want to go somewhere?
No, I was just thinking that we can make a celebration of Independence Day this way.
No, it was because we have a meeting together.
Yeah, yeah, but this is going to be after this one,
Okay,
right? Yeah.
okay. I thought that maybe you have to go somewhere and
No, no, I was just thinking that I'm going to make a treat to students.
oh, okay.
Yeah. Ah, tomorrow. Tomorrow. Okay, guys, are we ready to get started? Hey, sorry guys, I'm a little bit behind the schedule, so can we get started? Okay, respect. Very good. Yeah, it's like this. Respect. Very good. It's enough to say like this. Respect. Good. Okay. Last lecture of this class. So as promised, there will be a lecture next week, Tuesday too. But thank you guys. Thank you very much. But next week lecture will be off topic, so it's not going to be something that will be considered as one of the technical matters. It's going to give you soft skills. And I would like to give you a lecture regarding the career counseling. And more than a career counseling, I would like to give you a lecture about how is that I'm helping you to take the master thesis topics, and how is that I can, my instructions to you, how to select the topic that is appropriate for you. Uh, Somebody's calling me. I don't know who is this, so I'm going to pick up this a bit later. Anyway, so I wanted to give a lecture about how to select the master thesis topic, something that is related to financial support when you do your master thesis project. A little bit about what are the things that other matters that I'm hoping you to take into account within the next 5 years, because probably sometimes next year, or if not next year, at least in 25, you're going to get your master degree. And if you're hoping to continue your career in Finland, my instructions are related to that. So how to find the positions in Finland, and if you want to continue in academia, I will offer some instructions in that regard too. Okay, but off topic. Definitely not going to ask that to matter any of the details related to my next week lecture in midterm exam. Okay, how did you like the artificial intelligence and mechanical engineering, the visiting lecture? It was pretty good.
Good discussion.
Good. What discussion?
Mm-hmm.
So you discussed.
Yeah, more than usually here.
So you really want to hurt me. You really want to make me feel bad. So you can do the discussion, but it's just a matter of who is the teaching. So if there's a good teacher, then you can be very interactive and you can make your contribution. But when I'm here, nothing. So what? Oh, now I know because you're afraid of my big muscles, right?
Mm-hmm.
Okay. Yeah. Well, that makes sense. Makes sense. Makes sense. Okay, I got it. I got it. I look so scary. Yeah. Yeah, that makes sense. Makes sense. Now I understand. I understand. So, but regarding the subject matter, you feel that is something interesting. Yep. Now, yeah, this is going to be something we will continue next year. Next year, there's a class entitled a simulation laboratory course. We'll get back to that later today. But Greg's going to give lectures in 4 weeks in that particular lecture series. And it's all about how is that you can create the models using large language models, I mean these ChatGPT and others. How is it you can use a local ChatGPT, chat, large language models, and how is that you can use a control together with the models, controls based on artificial intelligence. These are the kind of exercises that will be available for your next academic year. So please consider to participate. All right, but a few things before we can wrap up this course. So two new subject matters. First one is flexible bodies. We opened the topic already 2 weeks back, but we were not able to close it. Today we're gonna close it, and then we're gonna discuss shortly about real-time simulation and games. And my plan today is actually leave earlier than 5:45. I would like to give you a treat for Independence Day. We'll see how it goes. But I know that the university is getting quiet already. People are going back to their apartments and homes, so we can close early today. All right, but flexible bodies, that's where we're going to get started today. And a little bit something we discussed 2 weeks back. So 2 weeks back, we discussed that a flexible multi-body system dynamics can be categorized to two different fields depending on magnitude of deformation you look at. So if the deformation is considered to be small, then there's a one kind of like family of methods you can use. And this family of method is most often used. And this is the family of methods that are based on the combination of finite element approach and multi-body system dynamics. So those of you that are not familiar with the finite element method, shortly stated, it is a method that you can compute the strength of materials, you can compute the deformation, strains and stresses using computer simulation. So it's a method that is based on elements, and elements are combined together using nodes. And nodal decrease of freedom is something that you're solving as an unknowns in a finite element method. It can be used in a number of engineering disciplines, but when you use that together with multi-body system dynamics, you use a finite element family or part of the finite element that is designed for structural strength analysis. And the structural strength models can be used almost as they are in a combination of multi-body system dynamics. How that works, that too is a subject matter that we will discuss in details in a very thorough way in upcoming academic year. And again, is this course, simulation laboratory course. All right, then if you're not comfortable with the assumption of linear deformation, then you can take the nonlinear effect into account. And that simply means that if you look at the cantilever beam like the one that is shown here, the drawing is not possible today. Okay, anyways, the scenario entitled scenario A, so that's a cantilever beam. And the scenario B is something that you are making an assumption of small deformation. And how can I know that? I know it because when I look at the free end of the cantilever beam, I see that the loading, which is imposed at the free end of the cantilever beam, the end of the cantilever beam stays in a loading line. So it's not moving at all in axial direction. This is an assumption that is coming when you are assuming the strain displacement relationship to be linear, which is okay, but it limits yourself to small deformation only. All right? And if you're not happy with this assumption, then you can use a nonlinear strain displacement relationship, and then you can take this axial deformation into account. All right, here is the big picture in multi-body system dynamics. So it all started already 80s, roughly that time. There were first computer codes available, and they all were based on the assumption that the bodies were rigid. So deformation were not accounted. And then it became clear that in certain applications, if you wanted to make accurate models, you need to take a deformation into account. And the deformation in the very first place was assumed to be small, meaning that the strain displacement relationship was linear. And this too becomes to be clear that even more accurate models are needed in special cases like tires, clothing analysis. So when you wanted to analyze, for example, the clothing behavior in a washing machine, clothing in general, parachutes, airbags you use in cars, and so on and so forth. So those are all these examples that you need to take nonlinear strain displacement relationship into account. And another example that is shown here is this. Moi. Okay. Joo, joo. Kun me huomattiin, että se tentti on päällä. Okei, niin no se ei ollut, se oli vahinko, että se oli päällä. Niin, niin se tulee päälle sunnuntai ja maanantai välisenä yönä. Okei, tolle suorat sille. Joo, okei. Tota, kerkisitkö sen jo niin kuin submittaamaan sitten? Joo, no se jäi kesken nyt sitten. Joo, se oli vahingossa meille jäänyt päälle. Me ei tiedetä minkä takia. Joo, maanantai yönä lähtee käyntiin virallisesti. So yeah, excuse me. So this was related to midterm exam. So because we learned just a few minutes back. Yeah, this is a guy that is guilty of that thing. So he's not your friend. Okay, so a few minutes back we realized that the Moodle midterm exam is live and live in Moodle page. And that was not the intention. This was an intense, mistake we made some time back. And we corrected that by hiding it. And now this student was complaining or just saying that, while she was doing the exam, it was on the sudden disappearing. And we wanted that to be disappeared until next week, Monday. It's going to be open at Monday night that is between the Sunday and the Monday. But we'll get back to that. I'm going to get back to that. So that's what I'm going to the recap, the summary part. Okay, right. So I was here, this historical aspect. So I explained that it all became clear that this linear deformation, small deformation is not enough. In certain cases, you need to take nonlinear deformation into account, like cables. And like I promised that if you would like to learn most of the papers that we've been busy in this team, LUT, there are a lot of papers that are related to how to describe large deformation. Oh, excuse me. I was in a barber shop. I don't know if you noticed it, but the idea is that I'm looking pretty now, and I was in a barber shop and I got all kind of hair in my throat. So that's why. Hopefully it's gonna be okay today. So I'm looking pretty good. Very good. All right. So the publication we have created in multi-body team in LUT, many of them are related to these large deformation cases. Okay. So we'll see how is my voice today. If I remember correctly, we covered this too shortly 2 weeks back. So one of the simplest ways to create the deformation or to describe the deformable bodies is to use the technique that is theory-wise based on rigid multi-body system dynamics. And the idea is that we can take multiple rigid bodies and connect them by using spring elements. And this is going to give you like a behavior that it resembles the behavior of deformable bodies. The beauty of the method is that it's theoretically very simple. It's just that, the idea is this simple. So if you have original beam-like body that you see in this slide, what you do then is that you divided this one single beam-like body to number of rigid bodies. And if you sum up the inertia properties of these bodies, it's approximately same than your original beam-like body. And then what you're going to do in addition to that is that you're going to introduce spring elements to each of the 6 directions between the neighboring rigid bodies. And these spring elements, so they will take a deformation and the motion in a 6 direction into account, or they will actually resist the motion in 6 the 6 degrees of freedom. And this is your definition, or this is your way to model deformable bodies. This is a method that is very straightforward to use, and you need no enhance or no modification to your multi-body code. But it comes with a problem because it's kind of limited to beam-like bodies only. I've seen papers that this being used in a plate-like plate-shaped bodies, but then the spring connection becomes to be very, very complicated. And there's a bigger problem here too. The bigger problem is that when you have these springs between the bodies, this easily leads to the situation that your model consists of high frequencies and low frequencies. And this is something that you wanted to avoid as much as you can. And why you wanted to avoid it? Because this is something that can lead to numerically stiff equations. A numerically stiff equation is a numerical condition that is not very favorable to time integration scheme. So it basically means that there's a very high frequency vibration. And this high frequency vibration is something that the numerical integration scheme is able to recognize. This may be making no significant impact to your response, but the integrator is able to detect it. And because it's able to detect it, it lowers the time step to make sure that this high frequency vibration is correctly accounted. And that's why the simulation becomes to be very, very slow. And simulating just a few seconds will take not forever, but it's going to take a really long time. So this is a combination of low frequency and high frequencies, something that you want to avoid as much as you can. Now, when you use this approach, you usually end up to have a simulation model where there's a low frequencies, and it comes when you think about the bending of the beam-like body. Frequency is typically less than 50 hertz, but then you think about the axial deformation between two neighboring bodies, frequency can be 1,000 hertz. So here's your problem. So you wanted to avoid this as much as you can. 1,000 hertz, 50 hertz is already away from each other, so this is not the good modeling policy. But simple approach, and it doesn't really need much of a knowledge in the theoretical background because it's based on rigid bodies. Here are the few examples. These are the examples that were modeled already more than 25 years ago, and they're beam-like bodies modeled by using this lump mass approach. It seems to work fine. And this, like here, this white-like body here, the white color body is modeled as a flexible body using this technique. It's still a fairly okay method when you're modeling cables. And here are this is a little too loud. Okay, so this is here a country crane. And when you look at the country crane here, there are cables that are, its operation is basically based on the cables. And the cables are very, very complicated to model using any other technique than the lump mass approach. Of course, this is at the moment there are better approaches, but this, at the time that this was created, that was almost the only method available. But yes, sir.
You said like these are already older models, but the newer hardware available, like do these problems get flattened out because you can just power them with like newer hardware instead of fixing them?
Well, this cranes modeling, what is really all this, like the one that is this hydraulic driven crane and this manipulator that you can see here. But this country crane is not this is fairly recent model. But right now there are better ways to model the cables. The ways that you can model it is something that is physically more accurate than this one, and its computation is more efficient. It is based on something that those of you that are familiar with the finite element method. In one of the family, very small subfamily within the finite element method is called something like arbitrary Lagrangian Eulerian formulation. It means that it gives you ability to change the length of the element. It's theoretically pretty involving, pretty demanding, but it makes it possible that while you're running your system, you can change the length of your element. And this is beautiful because that's exactly what happens here. So you can use just maybe one element to model from the pulley to the payload. And this element length will vary while you're operating the crane. This is a computationally fantastic method, very efficient. And you can have a lot of modes to describe this deformation, but theory-wise, it's a little bit involving, a little bit cumbersome. But the method, again, is called arbitrary Lagrangian Eulerian formulation. And it gives you this ability that you otherwise would not get, which is changing the length of the element. Of course, you can always change the length, but then you introduce the strain. So if I can take a beam element, then I can make it twice the length. There's going to be a serious amount of strains. But with is based on this method, I can increase and decrease the length without introducing strains. And that's why it becomes to be so powerful. That's the big magic behind. What is that you asked? I forget that already.
You can just like because you have to describe now a problem, like if this card gets slower, and like you also said that these are older models.
Yep.
And now, for instance, new NVIDIA cards, if they can just solve a problem like this because they just get
Right.
more and more powerful.
Right, but the NVIDIA, typically you need to solve the system by using GPU, not CPU. I don't know if you can hear the difference. CPU, GPU. Correct, correct. So that's so GPU is something that you need to convert all the computing to being a GPU. Typically not easy to say, but more difficult to do. And it's very good if you can parallelize your problem, if you can use a parallel computing. This is this is typically something that you cannot use a parallel computing that much. So, so you still need to use a CPU. CPU is typically used. And of course, you can have a CPU power quite a bit too. But, if you have a stiff problem, it's not going to help you too much. Okay, so that's where we are. All right. All right, then here's a summary about this first method. So computationally expensive. This is the method based on lump mass approach. Computationally expensive, can be applied mainly for beam-like bodies. There are exceptions, of course, but I feel they are a little bit artificial. Material damping is quite simple. Of course, the damping model and the material damping is something that you may not be that much interested in, but is not very advanced model. Easy to implement, easy to use. Theory is almost like non-existent. All right, another alternative is this. What we can do then is that we can take another look about the kinematics we looked in the very beginning of the class. Remember we made this assumption how we're going to create the kinematics, and it was based on the vector u-bar. The u-bar is the one that scans all the particles within the bodies with respect to body reference frame. That was where we started at. Now, if you have this vector u-bar, and when you describe the particle using the vector u-bar, we also said that vector u-bar is constant with respect to time. And that's why the body is unable to deform. But we can make that to be something that the vector u-bar is not constant. We can actually take this into account by using a method that I mentioned earlier, which is this finite element method. And with help of finite element method, you can define where the particle, a single particle, is originally located at, and the deformation you can compute by using finite element method. This is a beautiful approach because the deformation will be then with respect to your body reference coordinate system, which, when I'm cutting the corners a little bit, is the same than global coordinate system in the finite element model. Now, what's the difference between this and then a conventional finite element method is that our reference coordinate system is not standing still, like is the case of finite element modeling, but it is translating and rotating. But this is okay, because if we're going to describe the deformation with respect to the body reference coordinate system, all that is possible. And then motion of reference coordinate system is simply accounted by using the multi-body system dynamics. So we're kind of taking the most advanced things from the multi-body system dynamics, which is a description of body reference coordinate system translation and rotation, and the most advanced things from the finite element method, which is the describing small deformation with respect to reference coordinate system. And that's going to be a method that is called the floating frame reference formulation. Hello. Where the floating frame reference formulation is coming from the fact that actually we need to do something for our finite element model. Because if we're going to use the finite element model as it is, it's not going to match well with the multi-body system dynamics. And this is simply because of mismatching number of unknowns. In multi-body system dynamics, when we're describing the body reference translation and rotation, we need 6 or 7 unknowns. 6 if we're going to use Euler angles, 7 is if it's going to be Euler parameters. And when you have a typical finite element method, number of unknowns is 10,000, 100,000, million, 10 million. They don't get along well. One has a too many degrees of freedom comparing to another one. So what we need to do is that we kind of have to lower the number of unknowns in the finite element method. Now that's where we're gonna use something that is called modal reduction technique. Okay, let me see what I have here. The modal reduction technique is that, this is the big picture. You take multibody and you take finite element. This one here, if you see my pointer, which you don't, okay. Let me see if I can do the drawings today. Just a second.
You can see your pointers.
Yes, you can. You can. Here it is. But let me try to do something else here. Let me try to do the drawing. Here. Okay. Good. Now the drawing is on. All right. No, not willing to do that. I don't know why he's not willing to do the drawing. But anyways, the one that is in the left side, that's your finite element equation of motion, which is describing the deformation with respect to reference coordinate system. And the one in the right side is your multi-body system dynamics. So we're combining these things. And like I say, we need to do something. And what we need to do is that we need to reduce the number of unknowns, because typically this one here, if you finally see my point, this one here, this is a vector of unknowns. This consists of 10,000, 100,000, 10 million unknowns. And this is not good. So we cannot solve that many unknowns in every single time step. And what we will do is that we actually take a look at the properties of the deformable body. And we're going to conduct an eigenvalue analysis for our deformable bodies. And as a result of eigenvalue analysis, we're going to get natural frequencies and corresponding natural eigenvectors. And these eigenvectors are describing you the way the structure can deform, and they can frequency is telling you what frequency is a natural frequency of that particular deformation mode. It's kind of that we're looking the ways that the structure can deform. And using this technique, we are able to move another space, completely another space, which is based on how much each of these deformation modes are contributing to final response of the system. And now when I look at your faces, I can see that that what I'm just explaining is it's kind of, how can I say it in a polite way? It's
I think it's beautiful.
it's beautiful, but
It's extremely hard, but it's beautiful.
all right.
How we approach it.
All right, but this is something that, again, we're going to discuss in the next class when we are, the class name is Simulation Laboratory course. So let me just say this to you. So we're combining two methods, finite element and multi-body system dynamics, and prior to combination, we're going to reduce the number of unknowns by using modal reduction technique. How you do it, what are the details, you're going to learn that later. And that's how it goes. And then you have finally, when you have this deformation modes. Yes, sir.
For that course, do we have to do any basic course relating to finite element method?
No, not at all. So if you're not familiar with the finite element method, that's fine. It's even maybe better this way. Let me explain to you why. Because I heard, if you got your background in finite element method, I don't know, like if you explain to you in a way that there's like springs and masses and things like that, it's going to take you a while to learn away from that concept, because finite element method is not about that. It is based on polynomials expansions, the polynomials that are describing the deformation. And I'm going to explain it in a way that you will get an idea what is an inherent feature of the finite element method. So it's even better that you don't know that you know nothing about finite element method. That's how I feel. Because I'm going to get started from the polynomials, and I'm just going to spend that much time, because those of you that are familiar with that, you might know already polynomials and shape functions and stuff like that. But still, you need to know the basics.
It's in the laboratory course.
laboratory course. Which did I mention this already? It's no, no, number one course in the university. I mentioned that already. Yes, it's a, if you make a list of the good courses in the university, first comes the laboratory course, then comes nothing, there's nothing, and then then slowly other courses. Like this course, this one, simulation of mechatronics machines, somewhere average, so that's where it is.
Another question, Mike.
Yes.
If I take the course from finite element method in steel structure, there is a course like this.
Yep.
And if I take the laboratory course, does these two courses will complement each other, or
Yeah, they complement. No, they complement. They definitely complement. So the finite element method for steel structures is using finite element method in a certain application. And when we look at the finite element method, we're looking at in a general tool set that you can use anywhere you want. So that is not going to make your mind confused. I can guarantee you that. All right. But anyways, this is how it is. Here are the few examples that the deformable bodies are used. So this is this biomechanical thing that, tibia and femur bones are models as deformable bodies. Not because the deformation itself makes a major impact, but we model them as a deformable bodies because we wanted to learn strain and strain rates during the different exercises. Why? Because we know, well, based on the athletics, pro athletics, and based on the animal studies, clinical studies that bone gets stronger if certain amount of strains and strain rates is imposed to it. How we can know, like, what kind of exercise is good for your bone health? This is very, very hard question. And this kind of the models can make a prediction. If you do the exercise like this, it means like this and this kind of strain rates, and the medical doctors can then make an interpretation whether or not this is a optimal level. So that's what it is. Yes, sir. Is is frozen? Frozen. You mean my? Okay. Huh.
where is our YouTube officer today? How we
Yeah, it's something wrong in my. But I'm looking pretty good in this frozen picture. So should I keep it this way or? Uh, what happened to this guy? Seems that this somehow, because Mustafa is predicting all the time that my camera is gonna fail one of these days. So maybe he's right about this. Yeah, he's not able to. USB device not recognized. Okay, let me make this one more time like this. Nope. Yep, it works. So we're back in the business. Not yet. Wait a few seconds because there's a little bit of delay. All right. Here it comes. That's okay. All right. Remember when I mentioned about this model reduction. So what we do when we're modeling, here's an example about the tibia here. So when we're modeling the tibia, so we're modeling the tibia by assuming there's certain deformation modes. And these are the deformation modes that are coming from the real person. So what we did for that particular person was that we scanned that person uh, lower limb, lower body by using magnetic resonance images and computer tomography. So MRI and CT. And MRI was giving us a geometry of the bone, and the CT was capable to give us the density of each of the location of the bone. And based on that information, we created a finite element model with very high number of degrees of freedom. And we reduced the number of degrees of freedom by looking at the certain deformation modes. And these are the deformation modes we used in a simulation you saw a little while ago. So that was the technique that we used. And of course, this is more powerful in applications than other applications than biomechanics, because the biomechanics, the deformation It doesn't make that much of an impact of the response. But we wanted to model this as a flexible bodies to just to be able to measure the strain and strain rates. All right. So
This motion is actually amplified, right?
this is amplified, yes. So deformation is not going to be that severe. If it is that severe, you're going to get some damage to your bones. All right. Real-time simulation. Here's what I'm going to be very brief because there is this class that is mandatory for all the master level students, which is called something that each of the professors in a department of mechanical engineering are delivering lectures. What is that? Digitalized design. Is that the name of the course? Really? But that's the I'm referring to maybe not. I don't think it is that one because I'm referring to the course that each of the professors in the department of mechanical engineering are giving the lecture one at a time. Is it that one? Really? How come it's having that a funny name?
It's just took all the designing and production and all of the sectors and
Okay, okay, okay. Yeah, that's exactly the one that I wanted that I'm referring here. So the one that there's an introduction. And when I did my introduction, which was already a couple of months back, I discussed about this real-time simulation. I discussed about the different product processes. And what I wanted to do is that I wanted to give a little bit of an update where we are at in this regard. Of course, one thing I recommend you to do is that go and try the Sim Studio that is located not far from this place. This is for online participants. This is a place that is located between the building number 2 and 6, the corridor that combines the two different buildings. And this is a place that is open 24/7. So if online participants, you're going to make a visit to university premises, make sure you will test this Sim Studio. 3 different models available at the moment. One is a country crane, another one is a forklift, and then and the log crane is the one that is also available. Right there, right there. It's like 20 meters away from this lecture room, so not far from this place. Okay, but anyways, because this is already mentioned, I've got to be super brief here, and I'm not going to explain all the details. Just want to show you this. So when we're building the real-time models, we're taking each of these blocks into account. So we're taking, and this is what we discussed in this course too. So we're taking mechanics using the multi-body system dynamics into account. We are accounting the hydraulics, or if there's other means of actuators, those will be accounted as well. Of course, there's quite a bit of interest right now to make this combination of mechanics and actuators to be computationally more efficient. Why they're not very efficient at the moment is typically related to problems in hydraulic modeling. Hydraulic modeling is way more slower comparing the modeling of mechanical component. And of course, you can use a technique that is called co-simulation, meaning that you have one integration scheme for one of these boxes, another one for second boxes. And then you're changing the information every now and then, but not necessarily too frequently. And this enhances the computational power quite a bit. This is making quite a bit of difference. But also there's a lot of studies like how is that we can simplify more models related to hydraulic actuators. Maybe we can use the surrogate models. Surrogate models that is not necessarily based on physical equations, but are based on data-driven or data that is coming from physical models. So this is what is quite hot topic at the moment. And then there's a working process that, of course, depending what you do with your model. Control system that is needed too. But the big deal in real-time simulation is that now we can take a user into account. And user can be interacting with the model by using joystick or whatever is the control scheme. Yes, sir.
shouldn't be in the newest versions the control system also feedback to the user? Like shouldn't there be an error on that as well?
So there is a control system gives a feedback to user. Yeah, this is like even the cars, they have this thing that, if you are getting off the road, it's checking your, uh, give you a little bit like a feedback. Yeah, it is possible. And there's this haptic joysticks that are currently in market too. So if you're doing something really funny, it gives you the feedback through the joystick. It's possible. Yeah, you're right. So it should be one more arrow included such that there's a control system gives the warning to user. And maybe it could be based on augmented reality too. Right now, I haven't seen those augmented reality things much in the use at the moment. But right now, there's a lot of discussion about what about this different kind of the displays that are displaying information to your windscreen. So maybe this could be considered as a very early version of augmented reality. And people are considering how is it going to really help you or what? And I feel that they might help you. The pro operators are typically a little bit against those things, but the average operator could benefit them quite a bit. It's a good point. Is it Greg or what makes you to have that much interaction? The Greg explained you that it's okay to ask a question in a lecture. And I forgot to mention that in the very beginning of this class, right? Life changed. So what was a thing that changed your life? This class, Greg's class, Greg's class. So life before and after Greg's class.
We are using AI to ask the question.
Good, very good, very good. Okay, this is something that I saw it already. So it works like this. Oh, this is a little too noisy. Now this is all these components that we looked a little while ago, which is a mechanics based on multi-body system dynamics, hydraulics, which is not the surrogate hydraulics, but the real hydraulics, and then the environment and the user. Each of these components are accounted here. Control scheme. This system, the control is actually super simple, almost like non-existent because there's simply just the connection from the joystick to direction valve. That's about it. But again, as promised, I'm not going to go over these examples, but just show you that, okay, if we can have close representation of physics, this is something that can be used in a product development process. And it can be used in a product development process in a way that the customers could get involved in your process more heavily than in past. Now that it's possible to introduce new ideas to customers and ask them to try it. Please try it and tell me how you feel about it. So we can finally have a tool to have a better understanding what exactly the customers wants and what are their needs. And this is critical because, in the product development, in my mind, the product development purpose is to serve the customers as much as you want. And what the customers want at the moment is related to customers or kind of like expected user experience. That seems to be really critical thing. And user experience is something that is hard to take into account, like what exactly they want when they say nice user experience. And this is difficult simply because customers typically are not able to communicate in the technical details. So they cannot say that, actually, I want to have this hydraulic system like this and that. But they might say that I want to have a hydraulic system that feels this and that. So what the heck this feeling means? Now you can finally have a tool when you have physics-based simulation model that is operating in real time. So you can build the example, you can build the prototype and ask, okay, how it feels like. Is this what you mean when you say that you want to have this and that kind of the hydraulic system? All right, so the concept is this. Digital tools that are used to enhance the product development process are used to build the bridge between the customer and the product development team. So finally, they can have a common language, so they can have a better means of communication. And that's why the gamification and real-time simulation is very important. And they use it already at least in companies like Sandvik Mining and Construction, which is a big company. So whenever they get started in a new product development process, one of the first things they do is that they're building the real-time simulation model and they ask customers to try it. And if the customer likes it, then the project will continue. And if the customer hates it, that's it. You are not going to go any further in your product development project. So that saves a lot of time and effort. And then finally, you have a way to serve your customers better than before. Okay. All right, but this is it. So I'm not going to explain. This is a sim studio. User training is all stories. Then when you're running your simulations such that you take sensor signal into a CON, you're kind of synchronizing your simulation to real machine operation. This is something that we're working very heavily at the moment. And the idea is that we can have something that we can have a full understanding about what's the state of the machine. We can computationally estimate the quantities that are very difficult to measure. This bone strain is a good example that is very, very difficult to measure, but computationally you can estimate what it is. And of course we have this human representation as well, and they are based on, of course, AI. Okay. This is a thing. This is a recap. I'm not going to ask anything about Greg's lecture. You can forget about that. But I'm going to explain, well, I don't think you will forget about that because it was something that benefits your work, your studies a lot. And we get back to this in course simulation laboratory course. All right, and we're going to shortly discuss, the matters that I'm about to ask in a midterm exam is this embedded technique, still related to multi-body system dynamics. We're going to briefly, or it's possible we're asking something like concepts about the embedded technique. Modeling of hydraulics is the main body of the questions that you will see in the next midterm exam. Then there's a deformable bodies, not very important. Real-time simulation, not going to be very important either. But even though that is rated as a 5 stars, the main body of questions is related to hydraulics. Okay, so it goes like this. Remember that these are each of the items that affects your final grade. So written exam is only 35%. Weekly homework, another, 30%, simulation work, another 35%, and the bonus is you can possibly get 110 points. So that's how it is. And grading, the percentage-wise is the one that is put it in writing in a green font. I mentioned in my first slide, in my first lecture of this class, that the next midterm exam will be in week 51. This week is problematic week because that's a Christmas week. The 25th will be, 24th is a Sunday. 24th is a Sunday, correct? And Sunday, 24th already in Finland is considered as a holy day and is not a good policy to work in that day. So I'm thinking that what if you guys agree, so what if we just gonna make this exam to be available 1 week earlier than initially discussed? So meaning that this will be available next week, Monday at 00:05 or something like that, right after the midnight, in a night that is between the Sunday and Monday. Is that okay?
How about we change it a week later?
Week later?
Yeah.
So really you want to destroy not just your Christmas, but also your New Year's Eve.
There are many deadlines.
But so what's that?
The semester is supposed to end on the 15th anyway, so putting it 1 week earlier is beneficial for most, at least.
Good. So 1 week earlier. So is it really mentioned that the semester is supposed to close at 15th?
The 15th, 12th, yeah, I read this.
But I'm sure you have still exams in a week that is 18th of December. No? No exam.
The digital engineering is next one, which I have usual exam, but it's also like on the 15th then.
15th.
When finished courses like the exam next week, and if the last presentation we have it also on the 15th.
Really? Okay, so the week 51 is already a week that you have no other businesses. You have nothing there. Okay, all right. So, but are you guys okay with this changed? So let's change it. Okay, so like mentioned, again, same thing that last time. So 2 attempts. You have a week time to do your 2 attempts. Okay? I need to take this away. Now when I did that. All right, so this. Great. So here are the first is embedded technique. So don't spend too much time on that. So this was a method based on coordinate partitioning. So you select or you divide your coordinates to two different categories, dependent and independent ones. And the number of dependent coordinates will be the same that number of constraint equations. And the number of independent coordinates will be the same that number of degrees of freedom in your system. And then how you do that in the details is that you do the coordinate partitioning to your Jacobian matrix. When you do so, then you can impose your virtual displacement such that it's kinematically admissible. And what is going to happen to you when you use this technique is that you will get same amount of differential equation than the number of degrees of freedom in your system. So conceptually, very different than method based on Lagrange multipliers. Okay, so that was a method that was still based on the multibody system dynamics. And you need these different equations and different matrices to put together the equation of motion. But as mentioned, the number of equations that you have here will be the same that number of degrees of freedom. How come it's still making this noise when I put the...
It's animation.
Huh. All right. Okay. Hydraulics. Matters related to hydraulics is properties of fluids, lamp fluid theory. Lamp fluid theory is definitely the most important thing. So this is something that I'm expecting you to understand fully. Make sure that you almost can memorize, well, you don't need to memorize this first order differential equation that describes the pressure, but make sure you understand what that is standing for. What is each of the components, and what is a physical interpretation of each of the components. All right, flow types, modeling of hydraulic components, those would be the... Ha! I thought that I already put this like completely muted. Where they can come from? Speaker. Okay. My apology. I made a mistake, so I don't want to use. So let me just run through these examples, these different cases. Here. Where's my pointer? Here. Properties of fluids. Viscosity, which is not so important, but the bulk modulus you need to understand that describes the flexibility of fluid. And then there was this effective bulk modulus that is different than bulk modulus because the bulk modulus describes the flexibility of fluid. Effective bulk modulus describes the flexibility of fluid and each of the components that contributes to deformation or the flexibility of hydraulic actuators. So they are conceptually a little different. They're having the same meaning, but they have a little bit different approach. Those are the things. Sorry about this. And then, well, this is how we describe this bulk modulus, and it's all about relation between the deformation, how is the change of the volume, and how is the change of the pressure, and you can use this technique to describe this effective bulk modulus. Here's an example about the effective bulk modulus. Again, fluids plus components. That's what it is. Make sure you understand the difference between the bulk modulus and the effective bulk modulus.
Can I
Yes, sir.
one question? The bulk model, the E, what is that?
This is a flexibility of fluid.
Will that be given to us?
Yes, of course. If there's going to be computing, everything will be given to you.
Okay.
Don't get too confused don't focus too much about the computing, because this midterm exam is more about texts and questions related to material that we've been discussed.
Okay.
I'm not sure if I should say this, but this second midterm exam is easier than the first one.
You already said that.
Did I?
Yeah.
In the first lecture after the
Okay, now I'm very much afraid of that because I'm afraid that you develop the
Yeah,
up-nose attitude. Like, okay, I figured out everything a while ago. I don't need to, put any effort whatsoever because I know everything. I know everything here. And then you go to exam and you're, oh my God, now they're asking this. So how can I not know this? And so that's why I'm a little bit afraid of. It's easy, but still, don't develop Swedish attitude.
Okay.
You know, the Swedish attitude is up nose attitude.
Yeah.
Okay, all right. Now this continues over and over again. I'm unable to put it off. Okay, lamp fluid theory. This is the most important thing. So this is what you use when you discretize your hydraulic circuit within the volumes where the pressure is assumed to be equally distributed. Equally distributed because you get the one scalar value, so you cannot know if there's any difference in the pressure within this volume. You just cannot know that. That's what it is. And the equation that is used is, of course, this one. First order differential equation that is taking effective bulk modulus into account. Volume size, flow rate in, flow rate out, and change of the volume. Was it comment? No. Equally distributed. This is an assumption. Because again, you get, you have the volume this size. You're comparing the pressure within this volume. So this volume, this pressure is scalar value. It's a single numerical value. So it means that you cannot know if there's a difference here and here because you get just one number. This is a good example that shows that you cannot take these pressure waves into account. So if you have a pressure waves, that the pressure within this volume will be different depending where you are at within this volume. This we cannot take into account because we simply have one scalar value. That's it. All right, and this noise continues. And then the flow types. The flow types are laminar flow and turbulent flow. Out of the two ones, the more important is turbulent. 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 Laminar flow takes place when the pressure difference is small, and then the particles are traveling with a good order. In turbulent flow, they are whirling. So there's a whirling. That's why the relationship between the pressure difference and the flow rate is quadratically related. All right. Valve types, the modeling of valves. This is generally speaking consisting of two steps. First, you need to know the moving component, the location of the moving component, and then you can model the flow rate through. That's how it goes. And then example we used was different kind of simple components. And we modeled them by using this semi-empirical modeling approach. The semi-empirical modeling approach, unknown parameters we can get from manufacturer's catalog. Simple like that. And when you use that in direction valves, this is how it looks. Direction valve is a good example about when there's a two-step. First, you need to know where the spool is located. You model that by using this delay equation that is shown here. Once you know your spool position, the flow rate will be function of your pressure difference. And then there's three different scenarios depending where is your spool located at. Yes, sir.
I do have one question. So the sign of pressures,
Yes.
and after, I'm not sure what they call these
Apps.
apps. Okay, so they have the same meaning. Why don't you use that?
Well, because we want to use apps under the screw rod, and we wanted to do that because if not, then there's a possibility that there's a minus under the screw rod, and this is going to give you imaginary numbers,
Yeah,
and it's going to make your life miserable.
no. I know. I'm just talking about the other part.
Another part.
So yeah, the part that says sine PA minus
PAPT.
PT.
Yeah, it's just that it's
Yeah,
just to give you the direction.
it's basically the what is saying?
Yeah, the sign is only give you the 1 or minus 1.
Yeah,
So it's like
yeah. So that's basically telling you to
direction,
keep it
direction to call.
always in the plus sign.
Yeah,
And if it's gonna be
minus, then you simply change the direction artificially using the sign function. That's what it is.
oh, okay,
Yeah, the sign is taking just to take care of the direction,
okay.
nothing else. All right. And we discussed about the pump and the cylinder. Pump is the one that is producing the flow rate, and the cylinder is the one that is converting the pressure to mechanical force. Those are the two components. And that was about hydraulics. Deformable bodies, two different approaches. The one that is based on this lamp mass approach, where you take your body, define, divide that to number of rigid bodies, put the spring element between the bodies, and that's your model. Or you can model it by using the floating frame reference formulation, where you take a finite element model and multi-body model, and you combine them together. That's two alternatives. Okay? And then shortly we discuss about the real-time simulation. I'm not gonna, you can take a look at this from the class that was, again, this monster length name, digital design, manufacturing, and how you're doing today class. So you can take a look at that there as a reference in your mind. But this is something that is more about common sense than anything else. All right. Then this is my last slide. Simulation laboratory course. I hope to see you soon there. So it's going to be getting started in January 10th, if I remember correctly. Good. Yes, sir.
Will there be any mathematical problem regarding embedded techniques
No, no, no,
information bodies?
no, no. There's going to be, I mean, there could be a question related to that, but not anything you to compute. No computing. So you can forget about symbolic math software this time and focus on understanding the material.
And mathematics only from hydraulics.
Hydraulics, yeah, but it's still going to be moderate math. So amount of math this midterm exam is much less than in the first midterm exam. Okay. Do you have can-do attitude? Yes, can-do attitude.
No.
No, what?
Absolutely doable attitude.
Even better.
Yeah.
Absolutely doable attitude. Very good. Very good. Okay. This another class will get started in January. So hope to see you, at least some of you there. Oh yeah, yeah. Thanks for reminding me that. Next week there's going to be a lecture, but it's not going to be any of the technical subject matters. It's about the career counseling. Career counseling. I recommend you to participate because I'm going to keep my knowledge about how what I recommend you to do when you're looking different possibilities in the industry and in academia, and it's mainly industry Finland and academia worldwide. But no, yeah.
Your exam during the lecture and ask you question about the exam during the lecture.
So so can you? So what was it this again? So can you ask a question?
If you do the exam during the lecture and ask a question about the exam during the lecture.
I don't know. I got confused. So so is there doodle exam?
What we take the Moodle exam during the lecture and ask you questions from the Moodle exam.
No. Like I said, this is off topic. This is soft skill. Soft skill. I don't know why I think that I wanted to do this soft skill for you, but I wanted to do it. I wanted to do it.
So technically, the lecture will be more related to simulation work.
No. It's absolutely, it's your career,
Okay.
your life. I mean, that is not very important lecture. It's only about your life. Only about your life. How is that you can be successful in your life? How is that you can be happy in your life? So we're going to touch the subject matters like that. So I'm sure you don't like this kind of thing because, like I said, you figured out everything a while ago, including how to make your life to be happy and successful and this kind of things.
I have seen online that Finland is the happiest country in the world. So you are
Okay,
doing
so it comes automatic. Yeah, I'm going to share the secret. So unlike participant, I'm sure you didn't heard that comment, but there's a comment that the Finland is the happiest country of the planet. So I'm going to share the trick how we can make it happen. And you notice that it is not related to weather.
Of course not.
Yeah, of course not.
Or the sun,
weather is nothing.
or the cold, or the snow.
Maybe it is.
Is that happy?
Actually, I am enjoying the course.
You're enjoying the gold. Okay, very good. Okay, so let me close this one. So then we. Yes, sir.
What time should I open
Okay, so my entrance will be, okay, my channel 1. Okay, my entrance will be at 7:20, 7:20, 7:20, but I cannot guarantee if it is exactly that time.
When you are next line, can you do like you wash your hands in respect?
Like this. Respect. What if I do this to president, like respect? We don't shake, we do respect. We do respect. What's that?
He would think that you're going to kill him. Like, this is like a sniper.
Oh yeah, yeah. You know there are soldiers standing just behind him, so maybe they're gonna attack me. But that's okay because I have these big muscles again. So, and now you're laughing. So why? Okay. Thanks, guys. So this is it. See you next week too. About the yeah yes one more thing.
As always, could you explain the lamp mastery? It's like the most important point.
Lamp mass approach. Yeah. Okay. Remember this was something that
No, the hydraulic lamp mass.
lamp mass,
Hydraulic.
lamp fluid theory. Lamp fluid theory. Okay. Lamp fluid theory again is a differential equation that we derive that by when we look at the control volume and how much mass flow comes in and how much mass flow is leaving out. We use the simple math representation to see this equation that was his first. Oh my God, this is big, big. How can I'm not getting rid of this? This one. This one. So we were able to get this one. And we use this definition of bulk modulus during the derivation. But the derivation is not the point here, but it's more about what are these components and what they're representing to you. The first component is a effective bulk modulus, volume size, flow rate in, flow rate out, and the change of the volume. That is only valid in case of hydraulic cylinder. Or another component that the volume actually is changing. Yes.
So you don't need to understand the application, like how to use it, but more like what it is.
Yes, what it is and what it's standing for. Exactly. Good. You guys happy? Very happy. Very happy. Me too.
Finally, we reached the summit. No more bumps.
Oh yeah. So it was. So we were in a summit of this big mountain.
Yeah,
We made it. So we all survived.
yeah.
No complaints.
Almost
Did
all
we?
the class.
Almost all. You know, except that the class is half the size that it was in the beginning. But at least you guys survived. Good. All right. So let me close this one. And it's gonna be a sauna day today, like every Tuesday.
Sauna Tuesday.
Correct. Okay. Thanks, guys. We'll close this one. Not yet.